And good evening, AP Physics students. Mr. Gerson coming at you with another problem here, Chapter 11, number 16. Now, before we jump into this problem with both feet, let's talk a little bit about simple harmonic motion in general. So, all simple harmonic motion is basically motion that follows a sine or a cosine function. Okay? So, we can write a nice general equation for if an object's undergoing simple harmonic motion, its position as a function of time could be written like this: a times the cosine of omega t. I know this looks like a W, but it's actually the Greek letter omega, where a here is defined to be the amplitude of vibration, and omega is something we call the angular frequency. It's basically just your normal frequency, or the number of cycles per second, or vibrations per second, times 2 pi. And of course, we remember that the frequency and period are inverses of each other. So if I have 3 cycles per second, one cycle would take a third of a second, right? Because 3 and 1/3 are inverses. So let's just draw a quick graph here of what, that would look like for general simple harmonic motion, right? So here's a nice cosine function. I would start at an amplitude A. Of course, this axis is my x here, and this is my time. And after I've got through one complete cycle, that would be 1 period. All right? Okay, so that's just a little bit of background information here about simple harmonic motion in a very general sense. Let's dive into problem 16 here, okay? So this problem states that I have a mass, and the mass is on a spring, okay? And the problem states that the mass of this object is 0.60 kilograms, and the position of this mass is governed by the equation x of t is equal to 0.45 cosine of 6.40 times t. Okay? And then it asks us a whole bunch of things about the mass. All right? So part A, first of all, says what is the amplitude of vibration of the mass. And we could answer that, right? So the cosine function, the maximum it gets is the number 1, all right? So 1 times 0.45, well, the maximum amplitude here would be 0.45 meters. So part A is just kind of getting us warmed up here, asking us if we kind of understand some of the basics of simple harmonic motion. Okay, part B says, what is the frequency? Okay, so, well, I know that this guy in here, right, 6.40, is not the frequency, but it would be the angular frequency, omega, which would be 2 pi times the regular frequency. So, I think you guys can still see this here. The frequency would just be 6.40 divided by 2 pi, which would be equal to, if I plug that into my old calculator, I get 1.02 hertz, all right, or cycles per second, all right, is my frequency. So this is the answer to part B. That is the answer to part A. Okay, so let's keep moving here. There are more parts to this problem here. Part C says, find, what do we want to find here? The total energy. Find the total energy. Okay, so the total energy, of course, is equal to the sum of the kinetic energy and the potential energy at any given point. Now, here is my plan. I am going to figure out what the maximum kinetic energy is, And of course, when the object has the maximum kinetic energy, the potential energy will be 0. So really, your maximum kinetic energy is equal to the total mechanical energy. Well, how can I find that? Well, K max would just be equal to 1/2 m Vmax squared, where Vmax is the maximum speed our simple harmonic oscillator achieves here. Well, how are we going to find that? Well, let's see here. This is what we're going to do. I'm going to cheat a little bit here, and some of you will get what I'm deriving at, and some of you won't, and that's okay. So I claim that if this is my position as a function of time, my velocity as a function of time would look like this. I took the derivative, okay? What is the maximum value this gets? Well, sine omega t, the maximum value any trig function gets is 1. So I claim that Vmax is equal to the amplitude times omega. So that's my plan for how I'm going to do this. Now, I'm just taking kind of an absolute value here. When it comes to kinetic energy, it doesn't matter the direction of my speed, right? Kinetic energy is always positive. So I'm going to claim that, what am I going to say here? My total mechanical energy is equal to K max is equal to 1/2 m times Vmax squared, which would be A times omega squared. So plugging everything here, I would get 1/2 times my mass, 0.60, times my amplitude, 0.45, times omega, which is just 6.40, right? Times 6.40, my angular frequency, squared. So plug that all in, and I get E sub t is equal to 2.5 joules. Okay? So that's my total mechanical energy. But Mr. Kirsten, part D, Mr. Kirsten, there's so many parts to this. Part D says, what is the potential and kinetic energy when our oscillator is at 0.30 meters? So not quite the maximum amplitude, but almost there. Well, I'm running out of room here, but let's see if we can get this done here. So I'm just going to go ahead and cheat a little bit and tell you, I'm not going to derive it for you. I was going to, but I'm running out of time here. K, your spring constant, is equal to omega squared times m. And if you want to see a super quick derivation of how I got to that, here it is, okay? But if I claim this, I could quick find what K is in this problem, and I would get that K is equal to 24.6 newtons per meter. I could then find my potential energy by plugging in 1/2 k x squared, which would be 1/2 times 24.6 times 0.30 squared, and I would get a potential energy of 1.1 joules when I am at 0.30 meters away from equilibrium. Well, how do I get my kinetic energy? Well, I could go back and do a little plug in this equation, find my V, or I could just say, hey, my total mechanical energy is 2.5 joules, my potential energy is 1.1 joule. I know that the sum of potential and kinetic must be total mechanical, therefore my kinetic energy must be 1.4 joules. All right, nice work, AP Physics students. I'm just coming up on 10 minutes here, So my joke might upload to YouTube and it might not. But for the joke, I need to give you a little bit of background information. And that is about the Higgs boson. Mr. Kirsten, is the Higgs boson kind of a big deal? Well, I don't know. Let's see what Discover Magazine thought of the top 100 science stories of 2012. Guess what number 1 was? The Higgs boson. The almost statistically got it figured out Higgs boson discovered at CERN over in Geneva, over in Europe. And of course, to sell magazines, they've called the Higgs boson the God particle, which never made sense to me. I don't know. When they discovered electrons, did they call those God particles? I don't know. It's pretty cool, but it's just a particle. So anyway, the joke is about the Higgs boson. Are you ready? Here we go. So a Higgs boson walks into a Catholic church, right? The priest goes down and says, "Hey, you Higgs boson, you call yourself the God particle? That's sacrilege. You get out of here, Higgs boson." Higgs boson turns to the priest and says, "Hey, but without me, how can you have Mass?" Get it? Because the Higgs particle is what gives all particles mass, right? So, it's kind of a joke. All right, nice job, AP Physics students. We will see you in class tomorrow.